We're in for a treat today. Many of you have participated in various discussions about our large telescope aspirations. And those of you who aren't actively involved have read about it, may even have read some of the news stories of the last 24 hours. But somebody who's actually very deeply and actively involved in both the science and the engineering is speaking to us today. Andy Szentgyorgi is going to be talking about the Giant Magellan Telescope. Andy is a native of the United States from a Hungarian refugee background. He was educated at Stony Brook, where he got a PhD in physics, and at the University of Wisconsin, where he got his PhD in 1986. And during his time at Wisconsin, he made a transition into our field and completed a thesis on a search for very high energy gamma ray emission from Cygnus X3. He spent his career, first he had a stint at Columbia, and he joined the Center for Astrophysics in 1989. Been here for a while, Andy. He's now the Associate Director for the Solar, Stellar, and Planetary Physics Division. Andy is also the Principal Investigator for the first light instrument on the Giant Magellan Telescope. And by that, two firsts mean there are a suite of agreed first light instruments that were developed by the Science Advisory Council. But among those, the project selected G-CLEF to be the very first one to actually go on the telescope and actually see photons that come from the GMT. Andy is responsible for delivering that instrument. So with that, I think I'll hand the floor over to you, Andy. And no pressure.
Thank you, Charles, and thanks for the opportunity to tell you about the GMT. These are exciting times for us. This is a little bit infomercial and a little bit science. A little bit danger for me because, when you have to talk about all the science for all the different instruments, it's not always on your reservation, and I hope I don't mislead anybody. But I'd like to tell you about the GMT project first, the GMT telescope, and then the first light instrumentation, and a little bit about when this is all going to happen. So, not to insult anybody's intelligence, but in 2021, the GMT will probably be the largest optical near-infrared telescope in the world. And you have to ask yourself why we're doing it. And of course, first of all, what are, the fundamental driving science questions that we're going to try and address with this, frankly, very expensive facility? Why do we need such a big telescope to do those things? And why should we put it in Chile? And I think that within the scientific portfolio of the GMT, we can consider attacking, I hope I'll convince you, attacking the question, at least of whether there's bioactivity on planets other than the Earth. We'd like to understand how the universe started, how did a gob of gas assemble itself into the furniture we see today, variegated stuff that fills the universe, and where the first stars come from. And I think we've got a good chance with this stupendous facility of attacking some of these. Just to remind you why you want a big aperture, different people see this differently. Cosmologists want to look at the faintest, most distant things, the earliest phase of the universe. On the other hand, people like myself are probably more interested in getting stupendous signal-to-noise on relatively bright objects. I'm designing G-CLEF to actually be able to look at GL229. Not that we will, but we could. And finally, it's to be remembered that big telescopes produce sharper images than small telescopes. And when the AO is fully implemented, adaptive optics is fully implemented, it's going to produce unprecedentedly sharp images. We're putting it in Chile because Atacama Desert has the best seeing of any terrestrial location. The Atacama Desert has the clearest skies in the world. And then there's all this synergy with, oh, that's the wrong button. Well, let's go back again. There we go. Synergy with a number of frontier facilities, especially ALMA, LSST, SKA, and Magellan, which we'll use as the sighting scope. And so here's the site of the Giant Magellan Telescope on Las Campanas Peak. Over here you can see these tiny little pips of Magellan, and way over here the DuPont Telescope. It's 2,500 meters. It's not a super high site, but it has very low precipitable water vapor. Latitude is -29. There's one of the reasons we chose it is there's deep existing infrastructure for all the other observatories, so there are roads and dorms and stuff, although they'll be building new stuff to support the telescope. And as I say, arguably it's one of the best seeing sites on Earth. So that's all good reason to do it. Now, just a little bit about the partnership that's building the GMT. I do want to stress that the Giant Magellan Telescope Organization is building the GMT. Its interim president is Pat McCarthy. We've got a new project manager from JPL named James Fanson, who worked on the high-speed photometer, I believe, for HST, some other major programs. But it's a huge global consortium, the Korean Astronomy Space Science Institute, COSI, who are actually collaborators at G-CLEF, ANU, Australian Astronomy Limited, Carnegie, Arizona, Texas A&M, Texas, Harvard, Smithsonian, University of Chicago, and recently Sao Paulo joined. Not Brazil, Sao Paulo, which is it's kind of like Massachusetts joining, but not the United States. Except they're much richer than Massachusetts, I suspect. Anyway, so the telescope. The GMT telescope is based on the spun University of Arizona Steward Mirror Lab primaries. These are each 8.4 meters in diameter and have their 7, you can't really see them here, 7 1.1 meter secondaries, where the secondaries are fully conjugated to the primaries. Very important thing for ground layer adaptive optics. The coatings and everything we do with this will be consistent with operation over the whole band accessible from the ground, from 300 angstroms up to 25 microns. It's a very, very fast primary. It's f.7 with a net focal ratio of f8. And so the plate scale is a whopping 1 millimeter per arc second. That seems pretty huge, but when you stack it up against the other ELTs, it's pretty tiny and makes things much more convenient. The field of view without a corrector is 10 arc minutes. With a very expensive corrector, it'll be 20 arc minutes. And adaptive optics are intrinsic. The adaptive optics are implemented at the secondary, like the LBT, Magellan, and MMT. Smallest number of reflections for good efficiency, very low thermal contamination, and it's always available to all instruments that want them. It may even be useful to optical instruments. Just to show you how big it is, these are our COSI collaborators standing. They painted circles on their parking lot. They also painted circles on the parking lot at Carnegie. Andrea Dupree went out with a tape measure and found out our parking lot isn't big enough to do this. So, which is why we didn't do it. In some sense, the GMT is a scaling of the Large Binocular Telescope. Large Binocular Telescope wingspan is almost as big as the Giant Magellan. A little bit big, a little smaller, but it's huge. And it is composed of two 8.4 meter primaries, just like the GMT. However, the wrinkle in building the GMT is that each one of these primaries that's off-axis has a really complicated shape to actually polish. And so we started out making one of the off-axis segments to convince ourselves it was possible. It's no small beer. But that actually it took 3.5 years to get the first one out. There were a lot of surprises when you try and make an off-axis optic this big. And we're ultimately going to make 7 segments that we need and 1 spare. But the production pipeline is to produce one every 10 to 12 months, which I think we're sort of hitting. Things always go a little slower than you hoped. But today, the GMT1 is done. It's in a box. GMT2 is being either started polishing or being polished. GMT3 is being ground to near net shape. Casting is in progress for GMT4, and we bought the glass for GMT5. When I first saw those numbers, I thought we're going to build 5 telescopes. Anyway, GMT operates in 3 different configurations. There is what we call a direct Gregorian narrow field. There's a Gregorian position behind the primary. Well, they're all behind the primary. A position behind the primary, and there's a folded beam like a Naismith board. And so the direct, all by itself, the direct narrow field Gregorian position has a 10 arc minute intrinsic field of view, and that's probably where a wide field multi-object spectrograph will go. There is a folded port that's illustrated here where a tertiary folds the beam to different instruments, and a rotator can select a number of different instruments. I'll show that in a second. And that has a 3 arc minute field of view. And then finally, there is a direct Gregorian wide field, which uses refractive correctors to achieve a 20 arc-minute field of view that would ultimately probably be populated with a thing called manifest, which is a multi-fiber feed for other instruments. We did the design study for this corrector, members of Central Engineering and myself. The trouble is that this lens is probably, when it's built, will probably be the largest lens ever built for civilian purposes. And so this is a little more expensive than we thought it was going to be when we started out. So we're feeling our way forward on that. As I said, adaptive optics are an intrinsic part of the GMT. The adaptive optics are implemented with these super meniscus. These are 2 millimeter thick, 1.1 meter diameter mirrors sitting on voice coils, and that's where this is how the adaptive optics are implemented. There are some different adaptive optic modes. Obviously, without adaptive optics, we get the median seeing, which is about 0.6 arc seconds. We can also operate in what's called ground layer mode, where we correct the pupil of the telescope. It's not really super adaptive optics, but it's very wide field, and it probably improves the concentration 15 to 50%. Without lasers, you can do AO just on guide stars, the object yourself, or something that's within the isoplanetic patch of your science object, and that'll be provide diffraction-limited performance. And then finally, laser tomography adaptive optics will provide nearly entire sky coverage, up to 97% coverage at the galactic caps, where we only see one galactic cap, where the stars are kind of sparse, and there's some places you can't look. But anyway, just to show you what sort of improvement you get, this is a natural seeing simulated star field, and then you turn on AO, and you get something that looks like this, these beautiful airy disks. It's claimed that this will be 10 times better than HST. This is just a chart that shows you how compares AO at the GMT, the bottom envelope of this red patch with this sort of performance you get in an 8-meter telescope. Of course, diffraction limit is defined by lambda over d. So the bigger d is, the smaller the better your angular resolution is. And you can see that almost out to 100 AU, you'll be able to resolve things with 1 AU accuracy. That's pretty exciting stuff. The core of both the guiding and AO system is the thing with the inconvenient acronym AGWS, the Acquisition, Guiding, and Wavefront Sensor, that's being designed, prototyped, and ultimately built by Brian McLeod here at CFA. They've already done, as I say, it's required for us to be able to achieve that 97% sky coverage at the galactic cap. The way it works is a laser system does the initial phasing. The really important thing here is all of those 7 mirrors have to be phased to about 50 nanometers RMS. So there's a laser system that gets you within 100 microns, and then the AGWS takes over and ultimately phases things with plus or minus 50 nanometers. We had one test that demonstrated the capability to achieve this. This piece of iron is in a box, I believe at Las Campanas right now, and Brian's getting in a plane next week or the week after to go down and do a second generation prototype test. So that's it's really exciting. Without phasing, there's no real reason to build a GMT. The AGWS, this starts to show you what the instrument suite looks like. This turquoise thing is the Gregorian instrument rotator, and the AGWS sort of sits in the middle, has all these different probes that can be deployed around to pick up stars to control the phasing. One of the really exciting things is the spec for the guide on the GMT is 0.2 arc seconds accuracy, not precision. You're going to take this telescope and you're going to say, I want to point at a star, and you'll get there with 0.2 of an arc second accuracy. It's really enabling for a lot of things and allows you to go very, very fast. It's got to phase the primaries so that you can have diffraction limited performances down to 8,000 angstroms. It's also going to provide that wide field ground layer adaptive optics. And also you have to, since this is an ALDAS telescope, you have to provide field derotation. So if you stack the GMT up against all the other ELTs, the ELT and the TMT, it is the smallest of the ELTs. And where it really shines, and I think the thing, it's not the thing I think, the feeling is that what distinguishes it is its ability to operate as a wide field instrument. And the figure of merit here is the area of the primary mirror weighted by the efficiency of the mirrors themselves times the field of view divided by the seeing disk, or the concentration of the image squared. So one place we win really well is the efficiency. We only have those two. When in the wide field mode, we only have two mirrors that we bounce off of. So the typical reflectivity of a aluminum coating is 0.9, and you only have to square that for the net throughput of the telescope, whereas the TMT has 3 bounces and the EELT has 5 bounces. So you make the telescope real small, real fast. And so Rebecca Bernstein folds these numbers all together and says that actually for wide field performance in this figure of merit, we are considerably better than either the TMT or the EELT. So that's, we could argue about that. I'll buy anybody a beer that wants to talk it over, and there are other ways to think about it, but that's one line of argumentation. So once we have a telescope, we need instruments on it, and this is the order that instruments are going to be delivered to the telescope. There's a commissioning camera that I'll tell you a little bit about. It's really to validate the telescope, but I'm sure we'll find a way to use it for science. There's G-CLEF, the GMT Consortium Large Earth Finder, which we're building here. It's a high dispersion optical spectrograph. GMACS, which is like Prince's glyph. It's not an acronym, it's just GMACS. It's a moderate dispersion spectrograph in the optical that is similar to IMAX or DEMOS or BinoSpec. Then comes GMT integral field spectrograph, which is a moderate dispersion near infrared integral field unit. That's followed by GMTNIRS, near infrared spectrograph, which is a near infrared shell that rather remarkably does JHK, LM all at once. Real simple, small, beautiful instrument. And then finally, the last instrument, which I can only deconstruct with the acronym with it on the screen, Manifest, which is a set of optical fibers that will feed either G-CLEF or GMACS. So my goal here was to tell you a little bit about the instruments, tell you about what, outline briefly what the science mission of each instrument was, but then sort of give you one vignette of an example science program you might do with that instrument. I can't talk in detail about any one instrument. First issue is where the instruments go. As I said before, most of the instruments sit up on this lazy Susan that derotates the sky. The GMACS, which is a big Gregorian instrument, goes down here. And then G-CLEF, because it's a precision radial velocity capable instrument, has to go at a gravity invariant location. So it sits on this lazy Susan that never tilts at all. And so the fibers that feed it are deployed up here, and then I'll show you later, snake down to the spectrograph. So I'm obviously going to talk a little more about G-CLEF since it's my baby, and we all love it here, of course. And G-CLEF is a fiber-fed optical shell spectrograph, and it's a general purpose instrument. I mean, the fact that we made it precision radial velocity capable vexes people sometimes, but we just thought that we should be able to have, a broad passband to enable a large portfolio of science. But we thought making a shell spectrograph for a modern telescope that couldn't help you address exoplanet science issues, particularly at CFA, was folly. So it's precision radial velocity capable. And as I say, as Charles has said, it's the first light instrument at the GMT. Operates in 4 resolution modes. And it has an interface to a multi-object spectrograph feed. The slightly confusing modes are there are 2 resolution 110,000 modes. One of them has a fiber scrambler, which costs you some efficiency, but gives you exquisite radial velocity precision. For people who are for cosmologists in the audience who want to do damped Lyman alpha systems and want every photon they can get, we have the non-scrambled precision radial velocity mode that where we removed the scrambler. For mostly in pursuit of abundances, many different things. There's what we call a medium resolution mode at a resolution of 35,000. And then for people who just want all the light they can get and don't care too much about what resolution they're working at, there's the high throughput mode. The design of G-CLEF was shaped by, as I say, our desire to enable a lot of different kinds of science. So people in particular, the near-field cosmologists who want to study extremely metal-poor stars, abundances across the local group, really want blue response. So we pushed way down to 3,500 angstroms, which is extraordinary for a fiber-fed instrument. Cosmologists, people that want to study this issue of whether the fine structure constant and the proton-electron mass ratio changes over cosmological timescales, a program I find kind of cool, sort of out of the box, want all as much red response as they can get. Exoplaneteers who want to, find and characterize exo-Earths by precision radial velocity, and people who want to search for biomarkers want long-term wavelength stability scale, wavelength scale stability. They actually want very high resolution 110,000. And really importantly, and this is important also for the cosmologists working with gamma ray bursts, it's a fast instrument change speed. Because when you have a transit and you want to take a spectrum, during the transit, you don't want to have to spend an hour getting from one instrument over to G-CLEF. And then people who want to do detailed chemical abundance beyond the local group, there's a suggestion that we might be able to do AGB stars at a distance of Virgo. You need a long slit length so that you can feed it with a MOS, so you can do 30. That's an observation that take about 35, 50 hours. And so you want to do 35. You got to have a lot of stars at once. So multiplex is very important. So just a couple of science drivers from my perspective, my corner of the building's perspective. The coming TESS mission is a huge driver. The TESS instrument is a mission in the spirit of Kepler, except instead of doing 100 square degrees, it's going to do the whole sky. These are fairly small apertures. I think they're 150 millimeters compared with Kepler's 1 meter aperture. So it's only finding bright things. So over here you see encoded the Kepler discoveries in blue, and you see ground-based transit discoveries in green, and the prediction for what TESS will find is here in red. And you can see that these things are really bright. And this is a histogram of some iteration of the TESS proposal of the prediction for what we'll find. But those blue dots give us a pretty good feel for what those red dots are going to look like. And, this is very important because for the sorts of things we do with atmospheres and for the discovery of Earth 2.0, we really need bright things. We're never going to find, in the foreseeable future, we're never going to find an Earth-mass planet orbiting a solar-type star in the habitable zone at 14th magnitude, even with an ELT. You need a lot of signal to noise. Another kind of exciting thing that's come up since we first conceived the instrument is a science driver to search for biomarkers. This is something I copied from, or redrew from a Jim Casting paper that shows the evolution of the composition of the Earth's. Sorry if you guys were at the ITC launch. I think I showed this slide. Composition of the Earth's atmosphere as a function of time from the beginning of the Hadean period to the Phanerozoic. And you see that somewhere when light turns on in the Proterozoic, all of a sudden CO2 and methane start to go away, and oxygen starts to become a more significant constituent of the atmosphere. And the Cambrian explosion is about here. That's when interesting life really starts to happen, and all those bacteria that made the oxygen enable life as we know it today. Let me say that the detection of O2 is not necessarily smoking gun, but it's pretty good evidence. And I think that if we found some exoplanets had O2 in their atmosphere and others didn't, that would certainly motivate people to solve this problem. And it seems like it's a really doable thing. Mercedes Lopez Morales and Florian Rodler did a really superb study with everything in about what it would take to find O2 in an exoplanetary atmosphere. You know, what the probability that the transits would happen when the sun was up, and really have analyzed it in great detail. And so the important trick here is that O2 actually has a really nice set of features around 7,600 angstroms, where G-CLEF is a really hot instrument. And the thing is that you, of course, have this foreground telluric comb that you have to look through, but Ignaz Snellen pioneered a technique realizing that any star has a line of sight, intrinsic line of sight velocity, and of course the planet has a velocity too, that Doppler shifts these features out from under these features. And so this is a Cry-Res observation of HD 209458, where this is a radial velocity and this is time, so this is spectra stacked up. And this little scratch in that really is the CO in the atmosphere of that planet transiting in front of the star. And so Mercedes has done I think made a fairly compelling argument that this is good science. I have to show you some baby pictures of what G-CLEF looks like. This is behind, these are the primary mirrors up here. The light comes through the hole in the castle of the central mirror, is relayed to some fibers, the ends of the optical fibers. There's a guide system up here, goes into the optical fibers. Then the spectrograph itself is inside a thermal enclosure down here. The optical fibers convey the light in this energy chain to the thermal enclosure. You lift off the thermal enclosure, and there's an air handling system to make the inside isothermal. It's about 1/100 of a degree stable 24/7. 365 days a year, 24 hours a day. There's some thermal control panels. You control the temperature of a vacuum chamber. And then inside the vacuum chamber, there's a composite optical bench that holds all the optics. And then this is the actual stuff of the spectrograph. And these optics are held at a millikelvin always. Millikelvins, plus or minus a millikelvin always. So, just to emphasize, this is the work of many hands. I'm sure you either recognize your name or you recognize a friend's name up there at the CFA. Carnegie is a major contributor. COSI is also a huge contributor. They've been fabulous collaborators. University of Chicago. Anna Frabel is the chair of the Science Working Group. Harlan Epps designs all the optics for us at LIC. Our colleagues at Cattolica have been really superb, and Sao Paulo has gotten interested in helping us with the AO feed. The next instrument to come along is GMACS. GMACS is an instrument in the scaling of binospec or IMAX. So it can operate either in natural seeing or ground layer adaptive optics. Has a fairly broad passband from 3,700 angstroms to 9,500 angstroms. There was an idea to try and extend that to 1.3 microns, but I think that's been pretty firmly rejected. Its resolution can vary between, it has 1 million modes, 1,500 to 6,000. It has multiple slit masks, very high throughput. The spec multiplex is 25 targets at once, but they would like to, their goal is to get to 100. And it has, as I said, a multi-object spectroscopy interface provided by the Manifest or possibly a IFU capability. The PI is Darren DePoy at Texas A&M. There was a little, it's gone through, if you follow this at all, there's been some evolution of GMACS. It was originally proposed as 4 GMACSs for a really huge field of view. It was considered to be kind of expensive, so I believe it was the Independent Instrument Design. There was a panel, IDAP was the acronym, that chose the First Light instrument, said this is too expensive. So it was turned into a single spectrograph, but then Steve Scheckman and Xiaowen at Chicago decided that an infrared channel was essential. But after horsing around for sort of 2 years, they're back to the idea of just a two-channel red and blue optical instrument, and that's where they are today, going forward. This is a good place to just have a shout out about what the GMT does for spectroscopy. In this chart, what you see is these bars. At the top of the bar, that's the sensitivity, 1 hour 5 sigma sensitivity in microjanskis or AB magnitudes of an 8-meter telescope, and the bottom is the GMT. So you get something, I don't know, like a factor of 4 across the band where you're just seeing limited. Of course, when you turn adaptive optics on, you're not going as d squared, you're going as d to the 4th, and you get really dramatic improvement in the infrared bands. But the bottom line is that the GMT for spectroscopy, and you do spectroscopy with big telescopes, really is a dramatic increase over the existing apertures today. The science drivers, largely cosmological, dwarf internal dynamics of dwarf ultrafaint galaxies, cluster dynamics, redshift surveys. Now remember that we're going to be in the same hemisphere as both the DES and LSST. It's good stuff. First light reionization. But let me just, one case that caught my eye that I thought was pretty interesting is actually studying the distribution of cold gas around galaxies in the interval from Z of 2 to 4. And this is, for sort of familiar technique. This is from Adelberger in 2006. If you have some galaxy at some moderate distance, in this case it's for this spectrum is derived from a galaxy at Z of 1.2, and then there's a background galaxy at a Z of, this I think was 2.2. You of course see, you see the two they're right next to each other. They're 2 arc seconds apart, 17 kiloparsecs. The absorption features show that you're seeing gas next to galaxy B that's closer. And this is very interesting because we understand a lot about structure formation of dark matter, but not so much about the baryons. And this is the physics of how baryons collect, and then the feedback processes where the supernovae start to go off. Star formation goes on. Supernova, supermassive black hole starts to feed energy back into the galaxy. That's not as well constrained as the understandings of what's happening with the dark matter. And so GMACS really could do a massive synoptic survey in this redshift range, where it's possible that all galaxies have these massive outflows. You also would be able to study galaxies considerably fainter than L star, which is kind of interesting. Not easy to do now. And the concept design report says not only can you study the outflows from these galaxies, but you might be able to distinguish the inflow from the outflow, stuff falling into feed star formation and the black hole, based on the redshift measured in these spectra. This just shows you a little bit about how well GMACS does. This is an hour on CAC with DEIMOS. This is an hour with GMACS on GMT, and all of a sudden all of these things, these different metal lines, really pop out at you that they're just not evident up here. And then the other question is, are there enough of them? Well, it turns out in the interval from Z of 2 to 5, there are a lot of targets. I mean, this is really ripe for multi-object spectroscopy, and so this is, I think, what do we call them? Shovel-ready project. For GMT. It's just an example. The next instrument to come is an instrument called the GMT integral field spectrograph. This was originally conceived by Peter McGregor, who tragically passed on last year. And the leadership of this project is now with Rob Sharp. Peter was really an amazing guy. It's got very fine spatial scale, so it really needs adaptive optics. The passband is 9,000 angstroms to the end of K. It has a couple of different fields of view that it can be operated in 2 different resolutions, and 45 effective slits with this range of widths. The field of view is 20 arc seconds. It operates as an imager with a 20.4 arc second square field of view and 5 milliarc seconds per pixel. It's very high throughput, and I think you can believe that number because it's based on the NIF instrument that was built for Gemini and is a real work of art. Brief digression, some IFUs work really well and some don't. Brief digression from what an IFU actually does, I realize not everybody knows what an integral field unit is. You have some object on the sky that's spatially extended, and then you have this very complicated mirror. Making this mirror is the heart of the whole problem, that makes slices of this spatially extended object into a linear object that you then reassemble into a rich data cube that gives you both the spatial and spectral information about the object. But it's making this has to be a very fussy reflective optic for an infrared instrument, and it's really, really easy to get wrong. They didn't get it wrong with NIF. NIF will be excellent for galaxy dynamics, black hole galaxy mass relations, reionization, star formation. The classic sort of thing you would do with NIF, GMTIFS, excuse me, is internal dynamics of galaxies at relatively high redshift. This is actually some data from, this is Reinhard Genzel, and it's an observation of this BZK galaxy with the telephone number at 2.4. And so what you're doing here is you've got this amorphous thing. You'd like to find out whether galaxies form out of rotating disks or sort of chaotically merging systems with no coherent rotation. So you form these channel maps that are about 65 kilometers wide, and then you put it all back together and recover the velocity structure of the galaxy itself. This is a beautiful piece of work. It was done on the VLT with Symphony, but this is one of the brighter. It's a brighter BZK galaxies with a Z greater than 2. So if you want to do lots of them, you need a bigger aperture. Just to see how well this works, the GMTIFS team took a Hubble Ultra Deep Field image, imposed some dynamics on it, and then sliced it up again, and they did a realization. It's a 10-hour integration of a galaxy at Z of 1.6, and then modeled what it looks like at the Gemini IFU spectrograph, and it's pretty nasty stuff to have to analyze. If you repeat that observation on the GMT, you really get the whole picture. It's really transforming stuff. There's one other fact. This is Karl Gebhardt calculated this. If you want to study the growth of massive black holes and how they affect host galaxies, you like to be able to spectrally and spatially resolve the sphere of influence of the black hole. And it turns out that GMTIFS will be able to resolve the sphere of influence of every black hole in the universe as long as they're bigger than 5 times 10 to the 9. Now that's a pretty big black hole. I think that's like M87. So, but it's still sort of amazing to be able to say, we can see all of something in the whole universe. I don't know. To me, that's sort of a transforming thing. Next instrument to come along will be the GMT near infrared spectrograph. This is still, since we're getting to instruments that are more and more conceptual in their design. For some reason, they drew a picture of it. It looks like they've made the instrument rotator out of plywood, but and this has really a very animal look. You're afraid it would bite you or something. Anyway, GMTNIRS is, I guess I didn't put this up here. This is the creation of Dan Jaffe at University of Texas and the team that helped Dan build IGRINS, which is an HK spectrograph that's now on the McDonald 2.7 meter, and everybody seems to want on their telescope. It's a very, very successful instrument. Again, this has to be AO fed. It does the whole JHK window all at once. It's really simple. This part, it's a very economical, lean instrument. Has two resolutions, a single slit. Two resolutions. JHK are 50,000 and LM are 100,000, but that doesn't change. And they're still working on demonstrating that they can make an adequate immersion grading, but I think they're really, really close. This would be really great for all sorts of young star phenomena, stellar disks, can't spell characterization, can I? Exoplanet characterizations, studies brown dwarfs. Just to comment briefly about that issue of the immersion gratings, the core of this instrument is, in fact, an immersion grating. And the reason you love immersion gratings is because the dispersion of the grating is boosted by a factor, the index of refraction of the immersing medium. When the light is diffracted off the inside of this grating, but when it comes out, it's dispersed factor n bigger. For silicon, at these wavelengths, n is 3, so you get 3 times as much dispersion. So all of a sudden, you can have a very, very small beam instrument on a really, really big telescope. Very economical, in some cases just makes it doable. The problem is that immersion gratings are very hard to make. This is a chart describing the processing to a working immersion grating. And when you read papers about it, 2 inches by 1 inch, it's not uncommon. So GMT is still a little bit in R&D, but I think they're very close. Progress has been rapid and steady, and this is going to be a great instrument. If you're looking at, T-Tauri stars, there's just such a rich, this is the whole passband of GMTNIRS, a rich collection of phenomena you can study. If there's a magnetic field, if you have a resolution of better than 30,000, you can measure Zeeman broadening. You can look at the interaction of the disk with the high energy radiation from the protostar in the molecular lines of water and CO. There's just so much going on here that for protostars, it's going to be an absolutely transformational instrument. Another thing, I always come back to exoplanets. If you want to study exoplanet atmospheres, this is also a very powerful instrument. This is a model Travis Barman made of beta pic B, assuming that it's 1400 degrees, a 1 hour exposure, resolution 30,000. And the black stuff is the observation you would predict for this exoplanet. The dark blue line is a cloudless atmosphere, and the light blue line is a cloudy atmosphere. And it's pretty clear that you could nail this very rapidly with GMTNIRS. The optics look like this. There's a dichroic that splits the JHK and the L and M section. To compare it with the stalking horse of this sort of instrumentation now, comparing, I should say CRI-RES, with GMTNIRS, the little red dots are the limiting magnitude for CRI-RES. The green line is GMTNIRS. It's 2 magnitudes. It's going to be, and by the way, CRI-RES isn't actually operating right now, so shame. The last real instrument this is the most tortured acronym, the Many Instrument Fiber System for the GMT Manifest. And this is Matthew Collis and John Lawrence. And it's not an instrument, it has no CCD or infrared detector in it. It's just a thing that takes fibers from the focal plane of the telescope, either to G-CLEF or GMACS, or perhaps later in here, infrared MOS spectrograph. It's being prototyped. It's highly conceptual now. We're just now really thrashing out the real details. It's being prototyped as the Taipan instrument for the UK Schmidt, and as I say, it's still early in its development. It's a very funny system using something called star bugs. At the focus of the telescope, you put a glass plate, and you have these little vacuum chucks that have fibers coming out of them, and they're piezoelectric actuators that wiggle each one of these columns, and the star bugs then move around where you want them to go. Can this possibly work? Well, all I can do is, not only have I seen it work, but let's see, go back here. I have a movie, if I can only, how do you get the movie to go? No. that's a shame. There's a...
Try to move your cursor.
What's that?
Down. Try to move your cursor. The mouse pointer down.
Click.
Yeah.
Click.
And click, then you see.
See the arrow is down there.
Okay. I didn't try it.
There it is. Over
Okay.
there.
Oh, there we go. Okay, so you can actually hear these little... This is the telescope turning. And then they... It's kind of like shaving if you're an electric razor. And they actually go I mean, they're not going randomly. They're going where they're supposed to go. And I've seen that they can go straight uphill, so it's the damnedest thing. And, okay. So, manifest is going to be good for a lot of different things, obviously. I mean, chemical enrichment. Right now with the Hecto shell, we do internal dynamics of local group dwarf galaxies. With the GMT and manifest, you'd be able to do chemical, do abundances, chemical enrichment. The current state of the art here is shown for 8-meter apertures is shown in red, and you're really just capturing the tip of the AGB. I always sort of question whether the tip of the AGB is characteristic of everything else. And, it's the principle of the lamppost. You look where you can because that's where the light is. And this is where, in some cases we'll actually be down at the horizontal branch with the GMT. So that's going to be just really great science. As I said, that is really bad. It's still in a very conceptual phase. You could have massive IFUs feeding GMACS. You could have typically 40 or 50 fibers feeding G-CLEF. You could feed GMACS with small IFUs. If we ever have a near-infrared multi-object spectrograph, there are different things you could do. As I say, we're arguing about this right now, and we're nowhere near done. Last thing to talk about before I wrap up here is the commissioning camera. This is designed to validate the telescope, make sure the AO works and everything. But somehow an imager on the biggest telescope in the world, I think people are going to want to do science with that. And it's still in conceptual phase. Jeff Crane at Carnegie is in charge of it. But, it's going to have about a 6 arc-minute diagonal field of view, and will, at least is required to. Jeff's trying to make it a little bit bigger. Also, pixel sampling, a pass band of about 360 to 950 angstroms, and the rest is and it would be a direct Gregorian. A couple of stealth programs in the works, things we talk about. Be nice to have multi-object spectroscopy on day 1 with G-CLEF. So Joss Bland Hawthorne and I are talking about a plug plate, crude, ugly, for the most technologically advanced telescope in the world. But if you could do 40 objects at once, we'll do it crudely. It's worth doing badly. We're missing near-infrared spectroscopy, and so Rob Simcoe is thinking about a very simple fire-like instrument, near first light. And then, since GMACS is running a little late, Daniel Eisenstein has urged me to add capability to feed another, perhaps simple, moderate dispersion spectrograph for high-throughput cosmology studies. So, let's see, I'm almost done here. Now, I think this might be the first audiovisual, the first demonstration that is ever, probably not, done at a CFA colloquium. And so the question is why is Las Campanas called Las Campanas? And campanas means bells. And the reason it's called bells is because it's got this special rock up there. In plate you could find up there, it looks sort of like this. And if you take a rock and you hit it with a hammer, it makes a distinctly unbell-like tone. But if you find a piece of special rock, and you hold it just so, it rings like a bell. Hence, the bells, Las Campanas. And it's assumed that people, guanaco herders or llama herders, in the big storms pebbles would be flying around and hitting these rocks, making bell-like tones, and that's why it's Las Campanas. So the good news is we had groundbreaking on November 12th. They actually built this huge building on top of Las Campanas at the site of the GMT. And here's Charles with a hammer, hitting a piece of Las Campanas stone, making that bell-like tone. Also, here is the president of Chile, Michelle Bachelet, Taft Armendroff, chairman of the board, Miguel Roth, many of us know, Sharon Allen and Valerie Boyle in our development office, some board members, and most importantly, possibly the most popular television star, hemispheric television star, Mario Kreuzenberger, because there are many people who watch Spanish language TV than watch English language TV. And his show, Sábado Gigante, is the biggest show in the hemisphere. So, just to close out, when did this all happen? Do not try and reconcile this with the chart I showed you at the beginning when the instruments were arriving, because as we know, astronomical facilities are drawn on slightly elastic paper. Somewhere in 2022, the commissioning camera and G-CLEF will start operations with 4 primary segments and only static secondaries, no AO. Sometime in something like the 2024 era, GMTIFS shows up. We'll have all 7 mirrors, 7 static secondaries, and 4 adaptive secondaries. And I don't know how we're going to handle that. That's a story I don't have to tell. And then finally, somewhere in 2026, GMTNIRS and Manifest arrive, and we're in all AO mode, and the telescope I described for you is ready to use. But let's start thinking about it now. You start thinking about it, but first by bugging our board representatives to keep us informed, Daniel Eisenstein and Charles. You can also pester our SAC members, Dan Fabrican and Ito. Right, Ito? We also have a science working group for G-CLEF. Anna Frabel is currently the chair. Charlie Conroy and fielding the near-field cosmology science. Charlie Conroy is the discipline scientist for extragalactic astronomy. Mercedes Lopez Morales is the exoplanets discipline scientist. And Dan Stark is the high Z cosmology scientist. We're trying to get resources to actually really support, some postdocs or graduate students to help design reference missions. So when we get there at first light, we can do great science. And anybody who wants to participate, come pester me or come pester those people. The last thing is that there is free lunch. And every year now we have a community science meeting. There's no registration fee. There's a lot of free food and a really great banquet. First one was in Chicago on cosmology in the era of extremely large telescopes. Then there was a Washington meeting that Ito and I put on transient phenomena. That was a lot of fun at the American Indian Museum. There was a really nice conference at Asilomar in Monterey on resolving galaxies, extragalactic science in the era of extremely large telescopes. And as a topic near and dear to many of our hearts, there should be a special focus conference on exoplanets in 2016. And so, if I can just make the movie play, this one last movie play, with Giovanni's instruction, I was able to make this go. Now, what did you say, Igor?
The arrow.
Click it. Okay. Bill, let me turn the sound on. Well, you have to listen to it then, I guess. Oh, no, Holding instruments on the rotator, and there's a guy standing there with an attaché case. And we often think, why an attaché case? I'll stop there.
And we'll take questions.
Lights off.
Lights off, if possible.
It's a long movie. So.
Here it comes. No. Oh, the door's open.
The first publicity photograph shots that they had, the artists used the Los Angeles skies, these beautiful orange, smoggy sunsets with clouds on the horizon. Pat McCarthy is, no. I think we're about to see the attaché case. No. The GMTO has some cap, there are people that do that, They do this stuff for commercials all the time. Well, they start out. They had a mechanical engineer who was really. Oh, there's Attaché. He's talking on his cell phone, and you can see he's got. There's Attaché. They lifted it out of some stock catalog. So, okay.
I'll ask this uncomfortable question. As you probably know, there are some problems that actually appeared this year at last campaigns with the construction of new freeway with a lot of lights. Are there any plans to do anything about it before the GMT preparation?
Easy question to answer. I don't know.
I can answer it.
No, please.
Yeah, so absolutely, there's an intersection where the spur road from the Pan American Highway turns off and goes into La Silla and GMTO, and lights started appearing. It turns out that under Chilean law, for major intersections, there have to be street lamps, so the lamps are not going away. But there are discussions underway to apply what's been learned in Arizona about mitigating the sky brightness contribution of street lamps. It's not going to extend any further in the present range. It's not like the whole highway is going to be lit up. It's just for the intersection.
Okay.
So it's a concern, but there are steps which are reasonable being taken. And so I think, Roseanne.
Yeah, I mean, this is a fantastic project, very much in the spirit of these large missions that we do for space. So my question is, with all of the amazing science you can do, are there going to be some key projects that are encouraged? Or is it really just going to be that, let many flowers bloom and see how it all develops?
I'm going to let you answer that one too, since you're a board member.
Well, actually, this is something the SAC is addressing. Within the collaboration, we have partners ranging from Carnegie, which is very much the classic hero PI, go to the telescope, get your own data mode, through, let's say, more modern operations like ours, where remote observing and queue scheduling is under consideration. And I don't know if you want to comment. I'd say that there's no resolution yet.
No, I think this is one area of active discussion. Key projects versus the PI mode being one of them, but how to actually operate the telescope being a major point of discussion for the Science Advisory Council.
I'll take the extreme position. I think there's no more reason to go to the GMT than there is to visit Chandra, if it's built right. But that's one pole of that argument.
So I'd say as a board member and as the director of one of the partners, my view is that we should spend more effort in optimizing the visitor experience for potential donors than for scientists. The scientists should stay home, and people who can give us money should go to Chile. So I think that's a question.
Yeah, I have two questions. One is for the commissioning camera, the first instrument. Are we thinking in terms of a suite of filters so one could do some real science?
There is a position for filters. I can't find it, but Jeff is thinking about using it for science. Yes, I mean.
And the other one is, I know we talked about this in the past, but what is the present view of having an archive for all this wonderful data?
Everybody feels it's absolutely essential, and nobody wants to pay for it. But you can't have people taking data taken on a telescope that costs $300,000 or something, $150,000 a night, putting it on a memory stick and taking it home, and maybe getting around to reducing it. It's too precious.
Sorry. Yes.
For the first light camera and then further, but for the first light camera, will we have adaptive optics working to the short wavelengths too? And for all the others, we have 7 years or so to make the adaptive optics work at short wavelengths. We are claiming 2,000, we are talking about 3,500 angstroms of the short range.
Well, it's interesting you mentioned that, and I'm going to answer my own question instead of directly answering it. But Marcus Van Dam, who is the consultant who does all the modeling of GMTAO, we asked him to ask, and Brian was a participant in this too, you know, what would AO do for you down to 4,000 angstroms? And it's really quite striking. You know, for an optical fiber, it almost doubles the light into the fiber. You know, you just made your telescope twice as big. So that's huge. So I think, you know, from my perspective, we do want to push on trying to make AO work at shorter and shorter wavelengths. AO isn't going to show up until sort of the middle of the first light phase. And you're not going to have full up AO until, you know, somewhere in here, possibly a little bit later. But the commissioning camera is designed, in fact, to validate AO also. Right?
Yes, not at the diffraction limit though, for
Okay.
just for in the ground layer AO mode, I would think.
The commissioning camera, it has a point. It's 70 milliarc second plate scale.
Yeah, well, I don't know. I'm not going to say since I don't know all the details here, but
If it's 7 milliarc seconds, then it's not sampling the diffraction limit at that level at the short wavelengths. It's kind of killing it. So it's something to think about.
This is still also very much a conceptual phase. So, you know, you're welcome to have input into this.
but you won't achieve the diffraction limit over the field of view of the commissioning camera, no matter what.
Paul, this one, have you thought out the thermal environment to make sure that gradients don't affect your resolution? In other words, the building gets heated up during the day, but at night you open it up and if there's some gradients, thermal gradients, without provision, diminish.
We hire people that do nothing but computational fluid mechanics. We spend a lot of money on computational fluid mechanics. Not only simulate sort of static conditions as you described, the different wind incidence directions and what happens when you turn the slit into the wind at different velocities. So that's being addressed at as deep a level as you can. I'm never exactly sure how much I believe computational fluid mechanics has a covering solution to all those things, but it's certainly being addressed to the best of our ability. Yeah.
Okay, well, I think we've answered the questions that I can identify, so let's thank our speaker again.